Buenas tardes! May 23rd, 2019. Today's subject is Trisection, Pentasection, Heptasection, and unstretch for every natural n. Introduction. We know by Wolfram's and Alpha's powers that the cosine of 72 degrees is square root of 5 minus 1 over 4. The sin of 72 degrees is the square root of 1 minus cosine of 72 degrees squared. It is square root of 2 over 4 square root of 5 plus square root of 5. Who is cosine of 30? A1. It is 2 times cosine squared of 15 x1 minus 1. So we isolate x1. It is square root of a1 plus 1 over 2. Another goes similarly. The cosine of 72 is 2 times the cosine of 36 minus 1. Who is a2? Who is x2? The cosine of 36 is square root of 5 minus 1 over 4 plus 1 over 2. Again, who is the cosine of 36? 2 times of 2 cosine of 18 minus 1. Who is the cosine of 18? Here it is. But the cosine of 18 is 2 times cosine of 9 squared minus 1. Who is cosine of 9? Is x4. Now 3 times 9, 27. Who is the cosine of 27? 4x4 power to 3 minus 3 times x4. It is x5. Who is the cosine of 30? 1 minus 2 square of sin of 15. Who is a1? Cosine of 30. Who is y1? It is sin of 15. It is 1 minus a1 over 2 square root, where a1 is the same a1 here. It is or 1/3 the square root of 3 over 2. Again, the sin of 15, the sin of 36, the sin of 18 is at y3, the sin of 9 is y4. Now the sin of 27. Sin of 9, 3 times 4, 3 minus 4 times sin squared of 9 is y5. Sin of 27. y4 times 3 minus 4 times y4 squared. Now the cosine of 3. The cosine of 30 minus 27 is cos 30 cos 27 plus sin 30 sin 27. It is x6. The sin of 30 minus 27 is sin 30 cos 27 minus sin cos 30 sin 27. It's way 6. So we know who is cosine of 3 degrees. It is 4 cosine power to 3 of 1 degree minus 3 times cosine of 1 degree. This is classic. What is not classic is to divide the cosine of 3 by 3 to get cosine of 1 degree. This is what we're going to do now. Who is the cosine of 1 degree? 4z3 minus 3z minus x6 is equal to 0, where x6 is the cosine of 3 degrees. Z is the solution. The solution we will prove it is cosine of 1 degree. The second solution is the cosine of 121 degrees. And the third solution is the cosine of 2440 plus 1 degree. Okay? Let's use Cardano to prove that. x3 plus px plus q equals to 0, where p is minus 3 over 4 and q is minus x6 over 4. Who is x6? Minus 1 over 4 times square root of 3 over 5x. 5 plus 1 half y5. So we have to substitute the 5's. x5 is 4, x4 power to 3 minus 3, x4. And y5 is y4 times 3 minus 4, 4 y4 squared. And who are the 4's? Square root of 1 minus a 4 over 2 and square root of a 4 plus 1 over 2. Now go ahead and simplify. When we simplify, we join these, we get down these, we rationalize. Square root of 2 in the denominator is square root of 2 over 2. We simplify, we join the constants, we have a square root isolated, we have a parenthesis isolated. And now we're going to substitute a4. Who is a4? Square root of a3, a4. a1, a2, a3, a4. a4, 1 minus a4. a4 is x3. a3 is x2. a2 is x1. So here we have a2, x2. a3, x2. a4, x3. Square root, square root, square root. Here it is. Square root, square root, square root. Minus square root of 6 over 16. 2a4 minus 1. Here is 2a4 minus 1 minus square root of 2 over 16. The square root times 1 plus 2. 1 plus 2, a4. This is our q. And by Cardano's method showed in Wikipedia, we must calculate this delta q squared over 4 plus p3 over 27 equals to the same q, and p is 3 over 4, 27 over 64 divided by 27. So we take the GCD is 64 over 4, 16q2 minus 1. Who is W? It's the main cubic. The formula is minus q over 2, where q is that monster, plus I times square root of the opposite of this, square root of above, square root below. And it is the cube of z. Its argument is theta. The big W is its conjugate. It's z3, another complex number, power to 3. And the argument of the conjugate is the overline theta. Modulo of the square of the small w is q squared over 4 plus 1 minus 16q2 over 64. We cancellate modulo of z is equal to 1/2. Tangent of theta is b over a, imaginary part over real part. It is square root over 4q's negative. So overline theta is 360 minus theta. The argument of z is phi1 plus 120, phi1 over 2040, when we take the square root of w, where phi1 is theta over 3. The square root of w is 1/2 times the exponential of I, phi1 plus something. The argument of big Z is phi2, the same thing, where phi2 is over line theta over 3. It is analogous to 120 minus phi1, constant minus phi1, 0 minus phi1. Square root of big W is 1/2 the exponential of I, constant minus phi1. So x1 is the sum of the two square roots, the principal values of square root of cubic root of W. 1 degree, the small w, the small z, and minus 1 degree, the big Z. So we have cosine plus E sin. The imaginary parts cancel. 2 cosines over 2, 1 cosine of 1 degree. The other two may be discovered by Bhaskara, but we have this formula when we know Z and big Z. X2 is unitary Z plus unitary overlined big Z. So we have exponential of 121 plus exponential of 239, and they will cancel, and we will have the cosine of 121. It is the opposite of 180 minus 120. It is the minus cosine of 59. Similarly, 24/1. 241 degrees. It is the cosine of 241. It is the opposite of the cosine of, let me see, 24/1. We take 180 plus 60, 180 minus 60. It is well, you do the calculations and you will know that it is confirmed. Conclusion. Who is the cosine of t over 3? It's 1/2 of the principal value of the cubic root of the cosine of 3 times t plus I sin of 3 times t plus 1/2 the principal value square root of cosine of 3t plus I sin of 3t. And if you do the same thing for the cosine of 270 degrees minus t, all of that over 3, you'll get the sin of t over 3. What we're going to show now that this is for n equals to 3, can be generalized to n equals to 4, 5, 6, 7, and for all n. This is casus irreducibilis. We have two equations of third degree. We have solutions that are the three cosines. Solutions that are the three sines. And they cannot be reducible. They are algebraical numbers. So the cosine of 1 degree, the sine of 1 degree are algebraical numbers, because no, they are not algebraical numbers, because the cosine of 3t is not algebraical number, is? Yes, it is. All we have done above is to work with algebraical numbers. 1 degree is not constructible. By rule and compass, we have to straighten P, which is 180 degrees, and divide the straight P in 3 parts, and that's not acceptable. That's what the ancients do. But we have a family of algebraical numbers of 3rd degree. Now what we're going to show, that sin, the cube of sin of t, the cube of the sin of t minus 120, the cube of the sin over t minus 240 degrees also have a polynomial, which is derived by the Girard relations or Newton identities. We don't have to solve the equation to know. Okay? Let's prove the last equation. Who is a plus bi power to 3? Cosine of 3t plus I sin of 3t. The first is k. The second is si. A3 minus 3ab2 is k. 3a2b minus 3b3 is s. This is a system. The first equation, we isolate b2. It's a3 minus k over 3a. And the second equation, we power to 2. b2, 3a2 minus b2 squared is s2. Now we substitute this b2 is substituted here. We elevate this parenthesis to power 2 for let me see, 3a2 minus b2, here is b2 squared 9a2, here is 3a2 times 3a, 9a3, s2, s2, a3 is equal to x, to simplify, x minus k, 8x plus k squared, 27a3, 27x times s2, s2 is 1 minus k2, and the equation is proved. If you simplify, you will have x3 minus 34 cosine of 3t, x2 plus 12 cosine squared of 3t minus 27 over 64, x minus cosine at power to 3 of 3t over 64 equals to 0. And the 3 solutions, if you take it to the calculator, the cubic root, the arc cosine, it will be t plus constant degrees. Okay, exercise. Do the same for the exponential of I 270 degrees minus 3t. So you will have a formula for cosine elevated to a of t over 3 sin power to a t over 3. We choose power 3. How we choose power a? By Girard relations. Example. Here is the example. Let's go to the theorem of intersection. Theorem. The equations below are solvable by radicals. Cosine of Tn, 1/2 principal value of square root index n, cosine of nt plus I sin of nt, etc. Sin of a Tn, etc. If n is greater than 0, cosine of nt is this sum of cosine of t is powered to n minus 2i, y going from 0 to the integral part of n half of n. It's a polynomial of cosine of t. It's on Wikipedia named by Chebyshev. Chebyshev proved these constants. So whenever Pn of x is equal to 0, if and only if P of x is cosine of nt, if and only if the roots are cosine of t plus 2kp over n for k equals to 0, 1, 2, 3, 4 until n minus 1. And similarly, key n of x equal to 0 if and only if this p of x is cosine of np over 2 minus nt, if and only if the roots are the sine of t minus 2kp over n for k equals to 0, 1, 2, 3 until n minus 1, where Pn of x is the sum of I equals to 0 to n of alpha ni times xi, where the alphas are here. Example. Who is the cosine of 2 times t? 2 cosine of t squared minus 1. Who is cosine of 3t? 4 cosine of t to the cube minus 3 cosine of t. Now here is cosine of 4t, here is the cosine of 5t, and you study with more details on Wikipedia. Here is the triangle. The triangle says 2x2 minus 1 equals 2 cos t, 2t. 4x3 minus 3x equals 2 cosine of 3t. 8x4 minus 8x2 plus 1 equals 2 cosine of 4t. 16x5 minus 20x3 plus x5 is cosine of 5t. 32x6 minus 48x4 plus 18x2 minus 1 equals 2 cosine of 6t. 64x7 minus 112x5 plus 56x3 minus 7x equals 2 cosine of 7t. Exercise. Cosine of 1t is x. Cosine of 0t is 1. Exercise. Power it to a. We will know how to power it to a. And the sines are the same thing, where we substitute the cosine of nt by the cosine of np over 2 minus nt. We have to do the calculations, and is minus 0, minus 1, plus 2, plus 3, minus 4, minus 5, plus 6, plus 7. The exercise now is to construct two tetrahedra for cosine power to a and sine power to a. For each a and n, there is a polynomial. Here are the equations on trisection. We have known that the sum of the roots are 0. The sum of the roots 2 by 2 are minus 3 over 4. The product of the three roots is cosine of 3 over 4. And similarly for the sinus. He who trisects 3t also trisects 270 minus 3t and also finds 7 numbers. 3, 6. 6 numbers. Example, if we trisect 60, we will find 60 over 3, 20. We will find 20 plus 120. 20, 140, 20, 260, 20 plus 30, 50, because it's the complement. 20 plus 150, 170 is also a complement, and 20 plus 270 is also a complement. Now pentasection. The equations below are solvable by radicals. Nothing new. Here is the equation. Here is the solution. Here is the equation of sinus. Here is the solution of sinus. 0 is the sum of cosinus minus 20 over 16 is the sum 2 by 2. 0 is the sum 3 by 3. And 5 over 16 is the sum 4 by 4. And the product 5 by 5 is cosine of 5t over 16 minus. So we have the sum of sinus and cosinus is equal. At the end, it's different. The product is 1 of cosinus and the product of sinus is another thing. Exercise. Power to a the cosinus. How we power to a? Sketch of solution. When we know the equation of power 5, then we know what is that? Okay. We know the equation cosine of 5 times t over 16. From this to this, I subtracted cosine of t power to 5. x3 cosine of 3 power to 3. Cosine of t is x. Okay. All I have done there is x5 is cosine of t power to 5. But another equation, x minus cosine of t power to 5. It's x minus this minus this minus this, where t line is t plus 72 degrees. So we multiply x minus t line, x minus t2 lines, x minus t3 lines, x minus t4 lines. This is another equation. We have 5 x's. The solution of these equations will be cosine 1, cosine 2, cosine 3, cosine 4, cosine 5 power to 5. So this 5 is our a. It could be which a we wanted. Okay? So this will be another equation with another Girard's equations. We know the Girard equations of first degree. 0 minus 20 over 60, 0 minus 5 over 16, and minus 1 over 16 cosine of 5t. Who are the new sigmas? The sum of fifth powers, the sum 2 by 2 of 50 powers, the sum 3 by 3 of 50 powers, the sum 4 by 4 of 50 powers, and the product of 50 powers is the cosine power to 5 and 16 power to 5 minus 1 power to 5, 2 mega. Okay, 2 to 10 is a kilobyte, 2 to 20 is a megabyte. Okay, exercise sin power to a of t over 5. He who pentasects 5t also pentasects 405 minus 5t and finds q constants. K 0, 54, 72, 156, 144, 198, 216, 270, 288, 342. Because the complement of 72 is 90. 90 minus 72. No. Okay. 72 minus t. T minus 72. Minus 72 is 360 minus 72 is 288. Summed to 72 will give 360. So we have a theorem. When we have the equation x minus r1a, x minus rna equals to 0, theorem, let the polynomial equation be p of x equals to 0 of degree of p equals to n, whose roots are ri. Let a greater 2 or greater than or equal to 2 be a natural. Then, it's always possible to construct another polynomial q of x equals to 0 with the same degree n, whose roots are ri powered to a, without solving the equation p of x equal to 0 and only by using Girard's relations. Now heptasection. The same thing for n equals to 7. Nothing new. Here is the equation. Here are the solutions. If you substitute cosine of 7t equals to a fraction, you will have 7 algebraical numbers. They are cosine of a fraction divided by 7. The cosine or sine of that is an algebraical number because all of these coefficients are rationals. Main corollary. These numbers are algebraical numbers. Take the arc cosine of a fraction, t, divide by q or multiply by q a fraction. Take the sine, take the cosine. Power to a. A is in n. Algebraical number. Exercise Girard for 7. S1, S2, S3, S4, S5, S6, and S7 is P, the product of 7 cosines or sines. Until 6, they are all equal. The 7th, they will be different. Exercise, divide by 7 nt and power to a. Divide by 7 nt and power, take the sine and power to a. He who heptasects 7t also heptasects 90 times 7, 630 minus 7t, and finds key in 0, 90 over 7, 360 over 7, 450 over 7, 720 over 7, 810 over 7, 1080 over 7, 1170 over 7, 1440 over 7, 1530 over 7, 1800 over 7, 270 degrees, and 2160 over 7, 2250 over 7, 2. So, where is Hungerford? Where are the soluble by unsolvable by radicals equations? I don't know. All of these we are working are soluble by radicals. Their groups is not unsolvable. N-section. When we have that equation, let's turn back to the equation. N-section. The equation is P of x equals to cos of nt. Pn of x alpha ni times xi from 0 to n. So the alpha ni's are S1, S2, S3, S4, S5, Sn. And we will divide by alpha nn. Let's turn back. Dividing alpha n minus 1 over 2 to power 2 n minus 1. The sum 1 by 1. The sum 2 by 2. Sign of plus alpha n minus 2 over 2 power 2 n minus 1. The sum I by I minus 1 power 2 I times alpha n minus y over 2 power 2 n minus 1. And the product minus 1 power 2 n alpha n 0 over 2 power 2 n minus 1. Exercise. Construct a polygon of n equals to 11 sides, 13, 17 sides, 19 sides, 23 sides, any sides. All you have to suppose is that it's possible to straighten the angle P to a segment of complement P meters, P centimeters, and divide it by n and torsion. How is to torsion? The unstretch and unstretch. You stretch P, you divide it by n parts and the unstretch P over n. Okay? Who is cosine of nt? In the case of 23, you will stop in n minus 22. You will have x power to 23, 21, 19, 17, 16, 15, 13, 11, 9, 7, 5, 3, and 1. And we have coefficients 2 power 23 minus 1 divide by 2 multiply by n divide by 1 minus 1. And here is the formula, nothing new, where I simplified n minus 7, n minus 8, n minus 9, n minus 10, n minus 11. Where it is understood we have to factorize the factorial of n divided the factorial of n factorial of n minus 4, n minus 6, n minus 5, n minus 8, n minus 12, n minus 22. Okay? Over 6 factorial, 7 factorial. No. 2 factorial, 3 factorial, 4 factorial, 5 factorial, 6 factorial, 7 factorial, 8 factorial, 9 factorial, 10 factorial, 11 factorial. This does not depend on this 12. This does not depend on this 22. Our cosinus need not be integers. Our cosinus are possibly complexes. When cosine of z is complex, cosine of z is a plus bi, cosine of x plus yi is cosine of x, a hyperbolic cosine of y minus I sin of x hyperbolic sin of I. So a is cos and b is minus sin. So we have the identity hyperbolic cosine squared of y minus hyperbolic sin squared of I is equal to 1. It is a over cos of x squared minus b over sin of x squared, where u is cosine of x. So 1 is a2 over u plus b2 over 1 u minus 1. So multiplying by u minus 1, u2 minus u is a2 times u minus 1 plus b2 times u. So solve by u. Solve to u. Who is u? u2 plus u. Here is the minus 1. Here is the b2. Here is the a2. And here is the a2. Everybody on the right. Okay, everybody on the right, u2, u minus a2, everybody on the left, minus a2. Okay, delta is the square of this, minus 4 times 1 for a2. Who is the cosine of x squared? This is u is minus this plus or minus the square root of delta over 2, and cosine of x are possibly 4 numbers, plus or minus here and plus or minus the square root of the result. X might be infinitely many numbers. They are cosine of these 4 numbers plus 2p k, where k is an integer. And who is y? We know that hyperbolic cosine of y is a over cosine of x. So you have to take the argument cosine hyperbolic cos hyperbolic of a over ci. Example, who is the arc cosine of 3 plus 4i equals 2 w? We know the cosine squared of x is 13 plus, here 26. 26 plus square root of 26 squared minus 4 times 9. So we take 4 out, divide by 2, 13. 13 squared, 169. 164 square root of 10. Square root of 13 plus etc. And x plus yi is the arc cos, 4 numbers, plus I arc cos hyperbolic of 3 over the same thing. And I have allow confirmed with Wolfram alpha. The cosine of this thing is 3 plus 4i. Result in radians. Miracle. Exercise. Who is the cosine of nz equals to 3 plus 4i? We want to intersect this number. Who is w? The sin of nw is 3 for I. We know the bisectrix of the arc cosine of this and the trisection of a complex of the cosine of a complex number. Reduction of order. Whenever we solve a cubic equation, we are solving the system of sum of simple sum of squares, and sum of cubes. The solutions x1, x2, x2, x3 are x, y, and z. So we substitute in here. We will have a delta, and we have this theorem. If we know a single root of the equation cubic, the other two roots are s minus x plus or minus square root of delta over 2, where delta is this thing. For example, when we know the cosine of 1 degree, we know the other two roots, minus cosine of 61 degrees and minus cosine of 59 degrees. Why is this here? Because we can do it with any polynomial. By Galois theorem, let a less than 4 or greater equals to 4. We know if we know b equals to n minus a roots of the equation, a xn s1 n minus 1, etc., and 1 power 2 n and minus 1 power 2 n as n equals to 0, then the other r roots are functions of x1 xn minus a in the set y1 ya for all I in 1 2 3 2a. Proof. Divide the original polynomial by x minus x1, for example cosine of 1 degree. Obtain q. Another polynomial where we know who is the sums, s1 line, s2 lines, and so on. Now solve key of x equals to 0. So there exists a polynomial of second degree 2y2 that we take the sum, original sum, which was 3 over 4 minus cosine of 1 degree, and here cosine of 3t over 4 or 16. Let me see exactly. This cosine of 3t over 4 minus cosine of 1 squared minus this original sum times cosine of 1 plus q, the original q. Here is an equation of second degree. The first coefficient is 1. The second coefficient is sum minus cosine of 1 degree. And the third coefficient is function of cosine of 1 degree, the original sum, and the original q, sum 2 by 2. This is a reduction of order. And this might be done several times. Even if a is greater than 4, if we know the roots, we know all the roots, we can divide by a equals to 6, a polynomial of n equals to 23, and we'll have a polynomial of 23 minus 6 equals to 17 cosines, where we are doing a n section, a 23 section, but the coefficients will be monsters. Variation of parameters, I will not do that now. 104 algebra is a sketch of whenever. Theorem 8. Let K be a field and F in Kx a polynomial of degree n greater than 0 where characteristic of K does not divide the factorial of n, which is always true when characteristic of K equals to 0. Then the equation f of x equals to 0 is solvable by radicals if and only if the Galois group of f is solvable. So, our Galois group of f are solvable. Quoderat demonstrandum, out of charity there is no salvation at all.